Welcome everyone. So today we are going to continue our study of method of characteristics. So method of characteristics, but we are going to characteristics and we are going to do it for a quasi-linear case. Okay, quasi-linear equation. Okay, so let us look at what sort of equation are we talking about. So basically, we are talking about an equation which looks like this: a of x y u ux plus b of x y u uy equals to c of x y u. Okay, and u restricted to gamma is, let's say, phi. So this is the equation which is given to us, and we call it a quasi-linear equation because see, this is a non-linear equation. I mean, it's not a linear equation. That's what. But the coefficient of a, b, and c, this depends on it. This may depend on u. Yeah, so it's not a linear equation, but it's not a fully non-linear equation. It's just a quasi-linear equation because it depends on u. Here also u and here also u. Right. I want to solve this equation. Yeah. So I want to study the well-posedness of one. So essentially, in this case, well-posedness, whenever I say, I mean only the existence and uniqueness part. Okay. So the existence and uniqueness of one. That is what we need to understand. Okay, so for first of all, let us understand that given any equation like this, can we always expect that there is a solution for? Okay, so the question is this question: given one, okay, can you always expect a solution? Expect a solution. Okay, or a unique solution. I mean, first of all, let's just understand that if we can expect a solution, and then we can talk about uniqueness later, right? But the answer is this: do you think we can expect any solution out of it? No, no. Huh? The answer is no. Why? So the thing is, you see, so if let's take an example and see. See, u t plus ux equals to, let's say, 0, yeah, and u at the point xx is sine x. Let us take up this example. This is a very simple problem, right, to solve. We already know that if, let's say, gamma and phi, yeah, this is the initial data curve. If you want to write it in terms of a parameterization, this is r sin r. Yeah, this will lie on S, which is graph of u. Graph of u. I want to solve this thing, yeah. And C of S is the characteristic curve. Characteristic curve. Huh? S is parameterizing the characteristic curve. R is parameterizing the data curve. So R parameterizing data curve, and S is parameterizing the characteristic curve. Characteristic curve, right? Okay, now let us solve this problem. See, you guys already know, I mean, I am not writing all these characteristic equations and all because you guys already can do that. We saw it in the earlier classes. U of xt, if I just solve one, let's say that's 1 and that's 2. If I just solve one, what do I get? U of xt is some arbitrary function of x minus t, is a solution of 1. Solution of 1 for f in C1. For any f in C1, this is a solution. Now, for u to solve 2, we have, now let's say u solves 2, right? Now, if u solves 2, u at the point xx is sin x, so sine of x should be u at the point x, t equals to x, okay? And then you have f of x minus x. So that will give you f of 0 is sin x. Okay. Now, do you think that can happen? See, f is for a, if you want to write f is an arbitrary function, that is fine. But for one solution, f is fixed, right? So for a fixed f, u of xt given by f of x minus t is a solution. Now f of 0 in that case will be a constant. Yeah, f is a C1 function. F at the point 0 it's a function, right? So you just can take one value here and it's a constant, and that is equals to a sin x you are writing, and x is varying in whatever, I mean let's say in r. So that's a function. This cannot happen, right? So a contradiction. You understand? So you cannot find a solution. Hence 1 plus 2 does not admit a solution. Okay, let us understand what is the problem here. See, so just take 30 seconds and think about what is the problem here. Okay, see, the problem is this. Let's say if I am putting u at the point x0 is sin x, there was absolutely no problem. You can just write it as sin of x minus t. That's the solution. Here the problem is this. What are the characteristic curves? The problem is this. Let us explain what is the problem. The problem is problem. Look at the characteristic curve. What are the characteristic curves? Characteristic curves are given by x minus t equals to constant, right? Those are the characteristic curves. C is in R. Yeah. See, the initial data here is given along one of the characteristic. So c equals to 0, x equals to t is a characteristic, right? X equals to t. So x equals to t is a characteristic curve along which the data is prescribed, right? You understand? See, x equals to t. So basically, same coordinate x equals to t line. On that line, the data is prescribed, and that is why what is happening is f of x minus f, which is becoming f of 0, right? And that is why that constant cannot be equals to function. So essentially, what is happening is here, x equals to t is a projected characteristic. Sorry, this is the projected characteristic curve, right? So the data is prescribed along one of the projected characteristics, and that is why what you have, that is why you have this contradiction, right? So hence you cannot have the data prescribed along projected characteristics. So for here comes a concept of called a concept which is called a non-characteristic data curve. Okay, so non-characteristic. Okay, so you see the thing is this. What I meant by all of this is you cannot have data along any curve and expect the problem to have a solution. You understand? Okay, you need to have a data on a, so the curve gamma. So you understand, for the solution to exist, the curve gamma must be a very special curve. Okay, so let me write it like this. We say okay, gamma of R, okay, which is gamma 1 of R, gamma 2 of R. Yeah, this is non-characteristic, curve. Okay, if gamma is nowhere tangent to the projected characteristic curves. Right? Yeah. See, if gamma is one of the tangents, so here tangents is not coming because all of the projected characteristics are lines and the tangent to the lines are the lines itself. Okay. So if gamma is nowhere tangent, then we are good to go. Okay, so essentially what this means in case of a, so let me write it in this thing in case of a Quasi-linear equation. So what are the projected characteristics? It is basically this gamma 1 of R, gamma 2 of R, okay, u of gamma 1 of R, gamma 2 of R, which is phi of R in our case, times b of gamma 1 of R, gamma 2 of R, phi of gamma 1 of u of gamma 1 of R, gamma 2 of R, which is this okay, this vector field times minus gamma 2 prime of r, gamma 1 prime of r, this is non-zero. Is it clear? See, what is this? This is basically, I mean, this particular thing is saying, this is a normal thing, right? So this is basically saying that this particular projected characteristics are given by x prime, y prime. X prime is A, y prime is B. So it is basically saying that the projected characteristic curve, okay, sorry, the non-characteristic, this curve, the data curve is a non-characteristic curve if the data curve is nowhere tangent. It cannot be tangent at any point, tangent to the projected characteristic curve. So that is the relation. So this dot minus gamma 2 prime, gamma 1 prime, this has to be non-zero. Clear? And if this happens, then you can show that, so the existence and uniqueness theorem, let me just write down the existence uniqueness. Okay, we will do the existence uniqueness later. For now, I will just give you a short idea. So essentially, if gamma is non-characteristic, okay, then the problem one admits an unique solution, okay, near, so let's say r naught is some point r naught 0. Okay, so s equals to 0. Near s equals to 0, you take any fixer. So let's say that this is your data curve gamma. Okay, let's say that's the point r naught 0. Okay, so near the point r naught 0, you can actually find a unique solution for this problem, provided this gamma is a non-characteristic. So this is the existence theorem, existence and uniqueness theorem. We'll do it properly later, but for now, I mean, just keep it in mind. But please understand that the unique solution is near r naught 0. Okay, so basically in some neighborhood here. Okay, some neighborhood here. Okay, now, so this is the case. So let's say you are given a problem. First of all, how do you solve a quasi-linear equation? So let us take up an example and see how do we solve it. Example, let's say ut plus ux equals to 0. Okay, and u at the point x0 is x. Let's take this equation and let's see how to deal with this problem. So as usual, gamma phi, the parameterization will be given by r0r. Clear? Gamma phi is gamma gamma 1 of r, gamma 2 of r, okay, and phi of r is given by r in our case. Okay, so is the data curve on S. S is the graph of U. What is U? U is the solution of this problem. Okay, the graph of U, the surface is given by S, and the data curve R0R is lies on S. Okay, so the characteristic equations. What are the characteristic equations? As I told you, you see, this is exactly in that form, and we can use the whatever we have been doing up till now. Okay, so x prime rs, okay, this will be with respect to s. This is u, and so this is z. We will also define z of s to be u of xs y of s. Yeah. See, along the curve, whatever the height of u is, okay, x and y is in R2. U at the point xy, that is the height. So that is given by z. So that is, we are writing as z as like this. So x prime is u, and u is z, right? So this is z. And moreover, x at the point R0. So at the point s equals to 0, what is the value? It is r. Okay. Y prime rs is given by, this is t prime rs. T prime rs is given by 1, and t at the point r0, this is 0. Okay, because r, this is 0. Okay, and z prime rs is 0, and what is z rs r0? This is r. Okay, so that's your characteristic equations. Now I want to solve this equation. See, let's say this is 1, this is 2, and this is 3. So solving 3, what do we get? Z of Rs is R. Yeah, Z of Rs is constant with respect to S. Clear? At the point S equals to 0, Z is R. So Z is always R for all S, right? So solving 3, we get Z of Rs is R. Now let's put, now putting it 1, putting Z equals to R in 1, we have x of Rs is R. So x of Rs, if you just solve it, it is R S plus a function of R, right? And so if you put this initial condition at the point R0, this is going to be R. So this is Rs plus R. So essentially this is R S plus 1. Okay. And similarly, what is T of Rs? T of Rs is S plus phi of R, S plus some function depending on R, and since T of R0 is 0, so T of Rs is essentially S. Okay, so please check this part. If you are not convinced, please check this part. Now, if you put this value here, therefore, what you get? X of Rs, you get it to be T is S. Okay, so R times S plus 1. Okay, which is R times T plus 1. Okay, so hence the projected, let's write down the projected characteristic. What are the projected characteristic? Characteristic curves. Okay, what are the projected characteristic curves? They are given by x equals to R T plus 1. Okay, R is in R. So you see projected characteristic curves here, they look a little different. Huh? It depends on R. For now, let's take this initial condition to only restricted to 0 and 1. Let's just put that. Huh? Let's see what happens. See here, so this R only varies between 0 and 1. Okay. Let's put this restriction and see what happens. I mean, without that also it's not a problem. So in this case, what we will do is R will only vary between 0 and 1. Okay. Let's say 0 and 1. Yeah. I want to see what are the projected characteristics. So let's say the projected characteristic will be in xt plane. Yeah, let's see. So first projected characteristic corresponding to R equals to 0 is x equals to R equals to 0 is x equals to 0. Okay. So x equals to 0 line, x equals to 0. This is one of the projected characteristic. I mean, maybe I can use a red for this thing. This is a projected characteristic. Okay. Now the other projected characteristics is see R equals to 1, let's say. So x equals to t plus 1. Huh? X equals to t plus 1. So something like this. T equals to minus 1 this point. Huh? So this is x equals to t plus 1. This is another projected characteristic. And if R varies between 0, 1 and 1, all these projected characteristic, every projected characteristic will lie here. Okay, will lie here. These are all straight lines. Huh? I'm not very good at drawing, so you understand this. These are all straight lines, and this will all meet at this point, right? T equals to minus 1. This will all meet at t equals to minus 1. Okay, so these are all projected characteristics. So it will span the whole thing, and it will meet up here. Okay. Now the thing is, let us write down the what is the exact solution, and then we'll talk more about what is happening here. So the solution, and therefore the solution is given by, see what is the solution? Z is R, right? Z is R. Okay. So Z u of x and y is u of x s y s, which is z of s, which is given by R, right? And R is x by t plus 1. Okay, that's the solution. So this t obviously cannot be minus 1, otherwise this blows up, right? So t is greater than minus 1. Okay, so and this is evident from the projected characteristics. See, what is happening is this: along the characteristics, right? Along the characteristics, z is r, right? So z is constant along the characteristic. Clear? Along the characteristic, z is constant. So just think of the graph above. For every point here, what is the value of z? It is constant. Okay. So here, every point is constant. At this point, what is the value of z? It is, let's say this point is 1, right? For r equals to 1. Okay. So z equals to 1 here. Here also z equals to 1 then. Okay. But again, if you carry on along this line, z has a different value, but along this line, z is always constant. So let's say this is r equals to half. R equals to half. Okay, so along this line z equals to half, it's going, but when it reaches here, what is happening? It will be at t equals to minus 1. Where do you think this will go? You see, along this line, if it goes at this point, it will take half. It should take half. Along this line, if it goes, it should take 1. Okay, so what is the value of z at this point, or u at this point? Yeah, there's a problem, right? I mean, both the lines, they will intersect somewhere, but what is the value of u at the intersection? At that point, it is undefined, because along two different characteristics you are getting two different values. Okay, so and this is given by this. You can see u is given by this. Okay, so here you understand that things are getting complicated in terms of when you look at the quasi-linear equation. So u of xy will, sorry, u of xt, u of xt, okay, will be given by this. So you understand that at t equals to 0, at t equals to minus 1, the projected characteristic curves meet, okay, and forms a singularity, okay. Later in the course, we will talk about this singularity. This is a very important kind of singularity. We will talk about this singularity and we'll see how to work around all this singularity. Okay, so this will be done later. Okay, so now we want to talk about existence theorem. So essentially, what is so special about non-characteristics? We want to look at it into that. So we want to talk about existence, right? Yeah, so existence theorem. Okay. So, what is the existence theorem? So, essentially, let me tell you what is the exact idea. So, if the exact idea is to talk about this sort of thing, f of x u gradient u equals to 0, yes, and u restricted to gamma is, let's say, g. This sort of thing is given. F and g are continuous. Are continuous, okay, wherever they are defined. I mean, I am not writing all that, it is continuous. Now this is a I mean, very this is a general format of a PD, right? So let's say that's your one, and we want to actually we want to see that so f and g are continuous. So the question is, this question is, when does one admit a unique solution? And unique solution, okay. And whenever we talk about solution, we mean, of course, u is in c1 of omega, wherever this u will be defined, c1, such that it satisfies this, that u restricted to this gamma is some curve, okay, that is equals to g, yes. And of course, I mean, here you can think of this x. So here we can think of this x is in from omega, which is containing Rn. Yeah, we are restricting ourselves to R2, but the exact same thing works for Rn, and I mean, there is nothing special about it. Okay, and this gamma, so this is the extra assumption, x is in omega, which is in Rn, and n is greater than equal to, okay, and u restricted to gamma is g. So what is gamma? Gamma, see, if you are taking your domain to be open set in Rn, so gamma is any curve, any smooth curve, okay? We are talking about smooth curve in Rn such that gamma is the graph of some function, okay, graph of some phi. So essentially, what is gamma? Gamma, sorry, this is not a smooth. This is a smooth surface. Sorry, this is not a smooth curve. In 2 dimension, it is curve. In 3 dimension, it will be a smooth surface. Okay, it's a smooth surface in Rn such that u is equals to. So basically, you can think of u as a graph of phi, where phi is from Rn minus 1 to R. Okay, so the graph of a function from Rn minus 1 to R, you think of that graph. Okay, so that will give you a surface in Rn, right? And the information of u is given on that surface, and you are saying that you are looking for a function u such that when you restrict u on the surface gamma, then you get this function g. This is in Rn. Of course, when it is R2, then essentially you are looking for a, the gamma is just a graph of some smooth function. Okay, this is a smooth function. This is smooth C infinity, let's say. C infinity function from R to R. Yes, and so the graph of phi, so which is gamma, will be a curve in that case. Okay, a smooth curve which lies in R2, right? And then the usual thing happens. So x is in R2 in that case. Okay, right? Now the question is this: so when does one admits a unique solution? Now, if you remember, why are we suddenly talking about it? Because this actually. So this question. Okay, so please understand this question. This question. Okay, see, for a given problem, you want to talk about the well posedness of the problem. Okay, and this question covers the first two part of well posedness. Well posedness, right? Okay, now, so we want to prove this thing, and we saw that for any problem, just a small revision. Okay, so we saw that for any problem, let's say ut plus ux equals to 0, okay, and u restricted to x, and x is, let's say, sine x. Yeah, this problem, so there does not exist, let's say, no solution. Yes, you can show that. So it is not that, it is not a like a guaranteed thing that any problem like this will have a solution, right? Forget about uniqueness. There may not exist any solution because the data is given on the one of the characteristic lines. Yeah. So what can we do about it? We talk about non-characteristics, right? Okay. So let me give. So essentially, if you want to find a unique solution of some problem, something like this, yeah, something like, let's say, 1, then we have to somehow take into account that non-characteristic condition. So from there on itself, we are going to talk about the theorem which we deem as a uniqueness theorem. Okay. So the theorem which we want to say is state is this. So theorem. Okay. So this is the uniqueness theorem. Yeah, very important. So it says that if gamma is that curve, gamma is non-characteristic. Okay. So what is the non-characteristic? So basically, gamma is a non-characteristic curve, essentially. Yeah, non-characteristic or surface, whatever. For 2 dimension, I'm just writing. You can do it for n dimension also. Non-characteristic for the Cauchy problem. For the Cauchy problem. Okay, what is the Cauchy problem? For now, I'm just writing it to as a quasi-linear problem or semi-linear, let's say. Yeah, you can do exact same thing for a quasi-linear and a non-linear problem. Okay, so A of x, y, ux plus B of x, y, uy equals to C of x comma y, and u restricted to gamma is phi. Yeah. So see, here I'm just writing it for semi-linear. You can also replace it with a quasi-linear, or you can do it for a non-linear problem also. Correct? So if gamma is a non-characteristic for the Cauchy problem, you remember the non-characteristic condition. Okay. Then one can find local inverse, a local inverse of the function g of Rs, which is equals to x of Rs, y of Rs, okay, near is equals to 0. Clear? So what it means is, that is, for each R naught, yeah, we can find an open set V, yeah, containing R naught 0 and an open set U containing G R naught 0. What is G R naught 0? It is X R naught 0 and Y R naught 0. What is X R naught 0? Y R naught 0, which is gamma 1 of R naught 0. So it is gamma 1 of R naught and gamma 2 of R naught, right? Okay. Such that G from V to U is bijective. Moreover, let me write here, G inverse, okay, from U to V, yeah, is C1. Okay, so essentially what it is saying, if the non-characteristic condition is given, right, you can actually confirm that a problem like this, let's say that's your 2, a problem like this admits a solution. But the solution, so very important, please understand this thing. So before we prove anything, this is a small remark. The above existence theorem, okay, guarantees the existence of an unique solution, right? See, it is saying that there is a neighborhood of R naught 0 where the solution is unique, yeah, unique solution, but locally, yeah, see, it is not saying. So let's say you are, I mean, think about this thing. Let's say this is your domain, right? Yeah. So let's say the whole domain you are there, and the initial curve is this. Let's say that's your x-axis, yeah. Let's say that's your x-axis. This is your y-axis, and let's say that's your initial curve gamma. This is just an example, okay? Initial curve gamma. What this theorem is saying is, for an arbitrary problem, yeah, if gamma is a non-characteristic, right? If gamma is a non-characteristic for that problem, then you can actually find a solution, but not everywhere. I mean, you cannot say that the unique solution exists in the whole domain. That's your domain, right? XY plane. It may not exist in the whole domain, but you can say that there is a small neighborhood, let's say something like this, okay? This, in this part of the domain, okay, small neighborhood. I mean, this is just an arbitrary, I guess, pro. Okay, there is a small neighborhood like this where you can actually, I mean, corresponding to this, you have some U, right, and that will give you some small surface. So you can have a solution which is unique, yeah. So which is unique and it satisfies that problem, yeah. So it satisfies this problem, ux plus uy equals to c, and u restricted to gamma is free. U restricted to gamma is free only on this part, okay, only this, so not in the whole gamma, right? So just this part of the gamma, okay. So let's say that's your r naught 0, okay. So in a small neighborhood of r naught 0, you can actually say that there is a unique solution, yeah. You see, near s equals to 0, near s equals to 0. So s equals to 0, see, s equals to 0, let's say we start from here and let's say goes like this, yeah. So it is saying in a small neighborhood you can get that. You cannot get it in everywhere in the domain, okay? So it's always local. So please remember, any existence theorem, most of the existence theorems are always local condition, yeah. Right. So now we want to prove this thing. Now, how do you prove it? So before we prove this thing, as you can see from the statement of the problem, these are something to do with the inverse function theorems. Okay. So let's talk about inverse function theorem. Okay. So we need the inverse function theorem to be used here. So what does inverse function theorem says? As you know that inverse function theorem is one of the most cornerstone theorem in all of analysis. Okay, it is probably the most important theorem in all of analysis. So what it says is this. So given we basically are talking about a vector field, right? So let's say f is from omega subset of Rn, okay, to Rn be a C1 map, right? Okay, so you are looking at a, obviously, please remember, inverse function theorem is always from the same dimension. Dimension is same, Rn to Rn, okay? Be a C1 map with df at the point P naught, not non-zero, for some P naught in omega, okay? So inverse function theorem, what the gist of inverse function theorem is, you are basically given a function, C1 function, you want to see whether there is a inverse exists, whether f inverse exists or not, okay? Definitely this is not true for any given function, right? What inverse function theorem says is if the Jacobian of f, so if df P naught, df, so if the Jacobian of the derivative of f at the point P naught is non-zero for some P naught in omega, then there exists u containing P naught and v containing f of P naught, okay, such that f from u to v is bijective and f inverse is in C1. Okay, so what it says is, see, if you are starting out with the f which is C1, yeah, which you are starting with the f which is C1, very important. Then, and if the Jacobian at some point P naught is non-zero, if the Jacobian is non-zero, then what you can say is around that point P naught, you can have a neighborhood u, and look at the image f of P naught, you have another neighborhood v, such that f from u to v. So you have to restrict f. Okay, obviously u is contained in omega. Okay, so u, let's say this is a u which is contained in omega. U which is contained in omega and f of P naught which is contained in v, such that when you restrict f to u, okay, from there f to v, that is a bijective map. So basically f inverse exists, and moreover f inverse is also C1. Okay, so if you take f to be C infinity, f inverse is C infinity. If f is ck, f inverse is ck, with this property obviously. So this is important. Okay, now let us prove the theorem. Okay, let us prove the existence theorem. See, so proof of existence theorem. Okay, before we go on the proof, if you guys don't know this theorem, please read it. It is very, very, very important theorem, and the proof of this you can get it in Apostol mathematical analysis book. Okay, this is okay. Please look at that book. Right. So let us look at the existence theorem. So for existence, what we do is you first of all fix a R naught in I, whatever, yeah, in that interval wherever you are taking the parameterization. So fix a R naught. So what are we doing? You see, you fix a R naught here. Okay. So R naught is the parameter. R is the parameter. Okay. You are parameterizing the initial curve, right? And R naught is one of the point in that. Okay. So you see, we are defining and define. It is already defined, right? So we are just writing it like this: g of Rs to be x of Rs x of rs and y of rs, right? Y of rs. Okay. Now, therefore, Jacobian of g at the point r is, okay, what happens to this thing? This is the determinant, of course, of x with respect to r, with respect, so this is xr of rs, I am not writing all that, huh? And this is xs YR, YS. I hope you guys know all this. Yeah. And if you don't know, please just read about it. I mean, this is not very difficult thing to understand. The Jacobian is given by, you take the first component, take the derivative of x with respect to r, take the derivative of x with respect to s. This is of course at the point r is. Yeah? I'm not writing all that. Okay, let me. So this is at the point r is. Yeah? This is at the point r is. Okay. So this is given by xr ys minus xs yr, right? So this is there. Now see, at the point r naught 0, at r naught 0, let's say what happens? Jacobian of g at the point r naught 0 will be given by xr at the point r naught 0, ys at the point r naught 0 minus xs at the point r naught 0, yr at the point r naught 0. R naught 0. Okay. Now, what is xr at the point r naught 0? If you remember, see x. Okay. First of all, ys at the point r naught 0. You remember what is ys at the point r naught 0? See, xs and ys, xs and ys. Yeah. At the point rs is given. Okay. So now what happens is there is a. For this problem, yeah, I have skipped a little bit. You see, for this problem, given this problem, you can talk about, I mean, just go as we have done up till now. Okay, so you think of the characteristic curve which is parameterized by gamma. Okay, so the gamma is parameterized by the characteristic curve, and you can write the characteristic equation, right? If you write the characteristic equation, yeah, what do you think xs is? X with respect to s, okay, that is a, right, and y with respect to s is b, that we already know, right? So let us write down the characteristic equation. Okay, so this is there, so we have to calculate this thing. Yeah, let's say this is I don't know, maybe star. Okay, we have to calculate this thing. Now from the characteristic equations, one has xs at the point rs is a of x at the point rs, y at the point rs, right? And ys at the point rs is equals to b at the point xrs and y at the point rs. Yeah, this is the characteristic equation, if you remember. Okay, now this implies xs of r0, this is a of x r0, y r0, okay, and ys of r0, sorry, r naught 0, okay, so I am calculating at the r naught 0. This is b of x r naught 0, y of r naught 0. Okay, now what is a of x r naught 0 and b of x r naught 0? We have to understand that. Okay, so you see, this is a of r naught 0 is, this is gamma 1 of r and gamma 2, sorry, r naught, and gamma 2 of r naught, right? So gamma is parameterized, if you remember, it is gamma 1 of r, gamma 2 of r, right? So at the point r naught, it's definitely gamma 1 of r naught, gamma 2 of r naught. Okay, and this is given by b of, again, gamma 1 of r naught, gamma 2 of r naught, right? Okay, now again, you see, what is xr at the point r? So xr at the point r naught 0, what do you think that is? So x at the point r naught 0 is gamma 1 of r naught. So this is gamma 1 prime of r naught, right? And yr at the point r naught 0 is gamma 2 prime of r naught, right? Okay. So that is given. Now if this is given, you just putting all this, putting in star one has g r naught 0 is given by gamma 1 prime r naught, right? Gamma 1 prime r naught times b of gamma 1 r naught, gamma 2 r naught, right? Minus gamma 2 prime r naught, okay, a of gamma 1 r naught, gamma 2 r naught, right? Okay, you see, this is the start condition, okay, the Jacobian condition. XR is y1 prime r naught, ys is b of this, so that is why I wrote it like this, minus again this calculation, okay. So that is there. Now you remember, see, this is the non-characteristic condition, okay. Now and it is given to be non-zero, yeah. Non-characteristic condition is this, and it is given to be non-zero. So by inverse function theorem, okay, so this is non-zero, yeah, it is given because gamma is a non-characteristic and hence this happens, yeah. So by inverse function theorem, we can find a inverse. There exists an inverse of g near r naught and 0, right? Because at the point r naught 0, I mean, this is the Jacobian is non-zero, so there exists a neighborhood of r naught 0, okay, and g of r naught 0, where g is inverse, I mean g inverse exists and g inverse is c1, okay. So this proves that if gamma is a non-characteristic, okay, there exists a local inverse of GRS, okay, and this proves our theorem. So let me just end this part by just saying this thing. See, why local inverse is sufficient for this. See, if you remember, while solving this problem, let's say while solving a problem like this, you are getting some characteristic equations for which you want to find, you know, x and r, right? I mean, x prime is this, y prime is this, z prime is this, and you calculate what is x, y and z, and that calculation will come in terms of r and s, right? Yeah. So, and you understand that it is not always possible to invert those r and s. So it is not always possible to write r and s explicitly in the form of x and y, right? And this is where the inverse function theorem comes. So inverse function theorem says that of course it is possible to, you know, invert the theorem. So invert r and s in terms of x and y, but the inversion is only possible, and the unique inversion is only possible in a local neighborhood. Okay, in a local neighborhood of r naught 0. So what it means is in a local neighborhood of the, you know, the initial curve. Okay, r naught 0 is s equals to 0, right? So near the initial curve, you can actually say that there is a unique solution. Okay. So with this, we are going to end this part.